So once more, good morning, everyone. And let's have a look at what we did last week and where we went off. So we have talked about this guy here. This is the well-known balance of momentum with the in the linear framework. So we are integrating over the a reference configuration. We have the linear strain tensor here, the linear stress tensor, linear strain tensor. We have included the dynamic parts, that's the acceleration over here, and also the body force, which is kind of the acceleration that we call gravity most of the time here. And we have talked about that we can, we can neglect this part here most of the time when implementing in our PyFEMP framework, because we are relying on this so-called external part of the weak form to be implemented by or handled by the finite element solver. So later on, and you can be sure those formulas here are just what I derived with you guys last week, and therefore this is nothing new. And at a certain point, we could conclude that the element right-hand side vector, which is the one that we have to program in our finite element subroutine, could be computed in this way here, given in index notation. So last time, maybe that's the main difference between last time and today. Last time we have only implemented here the stationary solution for the balance of momentum, and now today we are looking into the in-stationary solution of the balance of momentum that includes this second term over here, which you guys have to implement today. And also we are using a viscoelastic material as also introduced last exercise. So this sigma here is not just a function of epsilon, but also of epsilon dot, the strain rate. Speaking of which, let's have a little recap on this. So this is like Hooke's law as you might implemented it before. It's the tensor product of a constitutive tensor T with the linear strain tensor here in this case, and we are using Folk notation, so the linear strain tensor here appears in a vector format. Also, the linear stress tensor is a vector format property here in this case. So we will extend this as discussed last time. So we will implement this part over here, where we add technically on top of the linear strain tensor, linear stress tensor from Hooke's law, an additional term here using this constitutive matrix D containing our viscosity parameter mu or eta mu times the strain rate tensor, here also in Folk notation. Okay, so that will lead to this sigma here, and the B matrix is of course straightforward. N is our shape function, A is our acceleration. So we talked about in the first exercise how to apply Newmark time integration to obtain the acceleration, even though we have a displacement finite element formulation where displacements are our primary degrees of freedom or our only degrees of freedom. So this is what we use to obtain here the acceleration. The formulas for the Newmark scheme, I'm sorry, are also given here in this sheet. By the way, this sheet is of course provided in Moodle, where you can see here the bullets can take any form of a variable. We will use today just the displacement as said. So the first formula here, bullet dot, will mean the first time differentiation of that quantity, in our case velocity, and here the acceleration. All of this done before. Also, last time we have talked already about the differentiation of our acceleration with respect, nodal acceleration with respect to our degrees of freedom, because we needed that in our derivation. And I asked you guys to make this differentiation here for the nodal velocities with respect to the degrees of freedom. So this time this is given here so that you can like benchmark or correct your derivations, because I cannot stress this enough. We will use these equations later on, and so you have to adapt. Like in the future, you will find another time-dependent variable, which is the temperature, and then you have to do the same for the temperature. So this is why it's so important that you understand the mechanisms that we apply here, so that you can apply that also to the temperature later on. Okay, so time integration here is also given. Maybe as I was down here, there is this strain tensor that you have to compute, the rate of the strain tensor. And down here, you can also find a little bit about this strain tensor. So we start, we start with the linear strain tensor itself, and the rate is of course defined with as the material time derivative. And with knowing all of these partial derivatives, and of course with respect to the reference configuration, not depend on time at all. So all those derivations, differentiations with respect to time for the reference configuration are zero. We can end up with the linear strain rate to be simply the symmetric gradient of the velocities, and hence the computation of the strain rate is analog to the computation of the strain itself, except that here we are using the gradient of the displacements, while for the strain rate we are using the gradient of the velocities. And this is reflected as well in the computation from index notation. So here, in this case, you can identify the interpolation scheme for the strain tensor in Vogt notation using this B matrix here. And when you compute the strain rate, this is exactly the same interpolation scheme, except that now you apply the B matrix not on the displacement matrix here, but on the velocity matrix. So pretty straightforward. So with this in hand, I think we are done with this equation, and let me put here another bullet. So this is of course what you guys need to implement today. So furthermore, we discussed you need the tangent to the element vector being the element matrix. And for all those derivations, we ended up at equation 16 here, which is the second equation which you need to implement today. We can see that here we have the matrix K over I and J. So also last time we have discussed that Ri is like within the, or if you think about the R vector as a vector of number of degrees of freedom per node times node sized vector, you can identify that there is an equal pair of entries for each of those nodes. Here, X and Y, meaning this is the right-hand side equation for the displacement in X direction, while Y is of course in Y direction. You can imagine, as discussed last time, a potential third degree of freedom per node being the temperature will lead to, for example, R theta here, and the superscript N will of course be related to the node number, and therefore this is kind of Ri here, which we will program in a loop structure, but I'm pretty sure you remember that from all the other courses. And the stiffness matrix is of course defined analog to this, so this means I and J over here are of course related to the tangent part for a node I and node J. Yeah, anything that we have to discuss in here? I think not, because D over here was shown in the constitutive law. We have these factors over here, which appear to be stemmed from the Newmark time integration and the concerning derivatives of Newmark parameters like the acceleration or velocity with respect to our degrees of freedoms. Shape functions are, of course, straightforward. And also here, the Kronecker delta or identity tensor in a different notation should also be no problem for you guys. Okay, yeah, so equation 16 is the second equation for today. You might have recognized your homework, what you had to prepare for today. I give you the reference solution here for the same reason as said before, so that you don't lose track, but I will not do this every time. So I expect, because now you have it in a very clear and written format, that you can use this material for further derivations. Yeah. Okay. Hmm. Ah, nice. Okay, so for today's exercise, I have prepared another boundary value problem for you to take advantage of the time dependency of your balance of momentum implementation for today. So the idea here is that we provide that we look at a truss. I think the initial configuration of that truss or initial mesh here is 2 by 2 elements. So the truss is loaded by its own body weight. So there is a certain body force. I think it is 10 or minus 10, better to say. The origin of the coordinate system is placed here in the middle. And of course, guys, as this is an advanced course, we can also think about units here. Yeah, you're all going to become engineers, and in the real life, everything is of physical quantity. So yeah, you can already try to work with units a little more. The truss here is, of course, a 2D idealization of something 3D for real, and we are using the plane string constraint here on this model. The truss geometry here is given by 1 by 1. So the body force was given here by, or the body acceleration, gravity is given by minus 10 meter per second square. These roller conditions here on the top means that we prescribe no velocity in no displacements in y direction. So, but it is still free to move in x direction. Only this midpoint here is fixed completely. Therefore, as we will see in the boundary value problem implementation in a second, you need to use just even numbers for meshing here in x direction, such that a certain point is always located here, so that you can, or node, finite element node to be precise, so that this node can be assigned with this boundary condition. And during the simulation, we will use to record the displacement in y direction of this node here on the bottom. So therefore, it is required that you have nodes along this line, and this is achieved by using just even numbers with number of elements in x direction. And I think, yeah, from the implementation from the Python file, we can in a minute identify all the other parameters. Therefore, let me stop share here. And let's have a look at the problem itself. So all the files here are provided for you in Moodle as usual. And also, I have every file that we discussed today in the same folder as usual. There is also this dynamic element template that I prepared for you guys. We will go through that in a second. However, I'm using here the reference solution just to show you what to expect from this boundary value problem. So lots of this was discussed before. There is this meshing command over here. So n should be an even number as discussed before. Material is added, and you see that the material vector that we provide is a little longer now. This is due to the dynamic formulation, which needs some more material parameters. Also more about that in a minute. And then we have just two essential boundary conditions given. The one here fixes this node as discussed completely in this command actually just in UX direction, but for an X coordinate of 0 and Y coordinate of 0, that would be this fixed node. And now additionally, we fix UY, so the displacement in Y direction for all the nodes with a Y coordinate equal to 0. Now, a little bit different to what we've done before. We have a dynamic analysis. That means that we need to do some time stepping. And here, if you have any problems understanding this, please first review the first code of the oscillator, single mass oscillator, because there we used a similar structure. So some parameters are given here like time and delta t, so the time step size. And I just use time stepping until number of steps is achieved. Animation equal to true, that we will see triggers an animation of our dynamic analysis. If you keep that to false, this will not be shown, which might be beneficial if you've seen the movie enough. Then you can get some more performance if you really don't spend the time rendering the animation. And then we have times and UYS here to be some vectors for our recording during the analysis. Once more, this was also part of the first exercise. So for time stepping, also this structure is pretty much the same. We have a loop here over all time steps. First thing we do is increment a time variable, and then we use the next step command as before, but this time the load multiplier stays constant with 1. However, the time is incremented, and then we use the time variable, which is actually incremented just a line above, to introduce to the FEMP calculation the current time. Twice Newton iteration is done here because we expect that with a correct tangent implementation, we need in the linear theory 2 Newton iterations to inspect our residual to be 0. And you can already see from my previous run here that this is the same output as before, and this seems to work right. Okay, within the time loop, we have the result now. We have achieved the solution, and therefore we'd like to record the Y displacement of the very node as discussed before. So what I did here is I used the nodal dov command, which was also discussed in previous sessions, where I used the node selector to select the node on X coordinate equal to 0 and Y coordinate equal to -1. Of course, selecting nodes is always done with respect to their reference position. So while this node moves or is expected to move in the simulation, we are also here just using the reference configuration to select it. And in the reference configuration, -1 means the node on the very bottom of our truss. UY here means that we are recording, or we are requesting the Y displacement to be given, and all of this is saved in UY. Furthermore, we append the current time and UY to our recording vectors, same structure as in this oscillator exercise. And now we have some part here for the animation. I think it is not required that you guys really understand it. However, you might see that this is indeed nothing else than a plot as we've done before, just wrapped in this animation and with some pause command and clearing. However, the next thing here is this plot show command, which is completely non-indented. So we are outside our time loop here. And in the end, this is a plot for our for our times vector. So we are plotting overall time of our simulation, all the u, y, s, so displacements of this node that we recorded over time. So if I run this once more with my reference solution here, there appears this window, and you can see that this body under itself weight gets elongated. You can also see that it's free to contract on the support and that it bounces back frequently. If you don't see the coloring, I think that I switched on just recently here. That's that is by introducing here this post name, but it's not required that you do this in the same fashion. So in this dynamic analysis, we introduce, of course, or we can see that there's some inertia in the system due to the initial elongation. And now you can really use the blueprint of the single mass oscillator problem. This inertia is transferred into strain energy and back to kinetic energy. And so you see kind of an oscillation here in this two-dimensional oscillator bar as well. So once this simulation is done by, I don't see anything further. Also notice that the residual is numerically 0, which is important as said before. Then you can, okay, doesn't wanna. Then you can close this plot, and then appears the plot that we introduce on the bottom of this file, which is a plot of our displacement over time. You can see it's kind of roughly resolved. So this is due to the choice of the time step size here. So if you decrease the time step size, that will use finer time discretization, and you have can also get a finer plot. Of course, for the same amount of total time, you have to also increase the number of time steps for that, for the cost of longer computation time, of course. Here we see as one important aspect that we have exactly the oscillation that we observe on the single mass oscillator, and that this will continue, let's say, for a long time. Because of numerical effects, there might be some damping involved, but it's not visible in this time span here. So this is what to expect from this dynamic analysis. There is one modification, because we have included now also our viscoelastic material law, which was not active by now, because this parameter over here, once more, we will go through this in a second, is actually our damping parameter, which was set to 0. If I run the problem again with this parameter non-zero, I provided here a suggestion for you, then we can also see that in the movie here, the oscillation is really like more subtle than before. And in the end, we can inspect from the graph in a second that using this viscoelastic material, we actually achieve a damped curve, and we will, or the system will come to rest eventually. Both of these displacement over time plots I provided for you in the Moodle course. So if you're looking for a reference solution for your implementation, feel free to take a look at this. If you're using the element template as provided in Moodle, the problem will not show anything, because of course the only load in this problem is the body force that we introduced by a material parameter. I think that I told you guys last exercise, and therefore it's like there is no load on the template element. The template element, however, let's take a look at that, looks very similar to the one before. And yeah, the first differences that you see is inside the element init function. So what has changed between this element and last time, where we have had only the stationary part of the balance of momentum, is that now we have some history fields. For history fields also refer back to the first exercise, and we have an extended material parameter names list here. So we have material parameters this time E and nu as before, but also rho, so the material density. This eta here is my damping parameter, and then as a material parameter bx and by. Okay, then the next changes are in the element ks, and I have left here the implementation for the stationary balance of momentum. I have switched the indices so that the formulas shall align with the document that I provided in Moodle. So please don't be confused by that. I hope this is actually beneficial in your case. Okay, what has changed furthermore? Here in the beginning, I read in material parameters, which are a little more than before, and I form a vector B with our body acceleration. So a body acceleration vector. We have talked about this pattern here last time because this will build up our nodal coordinate and nodal displacement vector as we are used to use it. The same is provided by this line here, where we have taken from the history field of the element the variables in a structure that we have a nodal acceleration matrix, same structure as nodal displacement. Here the n means this is the variable from the last time step. I will refer back to time dependent and Newmark scheme stuff if you don't remember what this means. Also, you have here a second part which looks similar. This is like once you have computed the current acceleration and velocity, of course, the current displacement doesn't have to be computed. They are just given by the finite element. And those are shifted to the history field for knowing in the next time step. This structure you can easily see from the single mass oscillator problem as well. You already see also here the first task that you guys have to do today, implementing the Newmark time integration for achieving here the nodal acceleration and velocity. Everything else regarding time stepping or time shifting of those variables will be provided by PyFEMP. Okay, so everything here, I guess, was discussed intensively last exercise. You have to extend, of course, a lot of things there today, because if I look at line 153 here, this is definition of or implementation of the right-hand side vector of this element with the concerning part from the balance of momentum in the stationary case. This has to be extended now according to formula 10 from the sheet that we discussed before. So of course, if this right-hand side now involves something like acceleration, as it does, this acceleration has to be computed, of course, before using it here. That's also your task. The sigma that you see here, so the linear stresses that I used are also different than last time. Remember, we are using this viscoelastic material. And of course, in the end, the correct tangent has to be implemented as well. Okay.